Good afternoon. Welcome to Lecture 2 of the Kalman Filter Basics lecture series. Today we will be looking at a handwritten, simple example of using a Kalman filter to filter out a noisy thermometer data. So what will you learn in this video? How a Kalman filter can be used to filter thermometer noise. Note that this is a very simple example, nothing complex, and hopefully you'd have an appreciation for the Kalman filter. So last lecture we looked at the equations and what the Kalman filter was for. Today we're going to have a little simple handwritten example that you can work along, and so you can hopefully appreciate the Kalman filter a bit more. So a scenario, so of course we're not just going to calculate random stuff. So a scenario, you have a thermometer and you want to measure the temperature of a temperature controlled room. Now the room always sustains 15 degrees at all time, so it doesn't really change. But your thermometer is actually low quality, it's very low quality and it's quite noisy. So it's not going to always read 15 degrees at all time. It's going to read something, a bit of jitter and some random noise in there. So in this scenario, we're going to use a Kalman filter to correct the thermometer data. Now, remember from last lecture, these are all the equations. Of course, when I handwrite them, I'll write them all down for you, but here's what they look like. You predict, then you do your estimation stage. Now, some key assumptions. Remember that we have to make a model, so a Kalman filter requires a model. So for simplicity, of course, we don't want to spend hours calculating and sheets of paper. So we're just going to use a constant model, which means that the next prediction equals the last prediction. Now, a Kalman filter requires some initial assumptions too, if you remember. So of course, the previous prediction at time equals 0 is an initial prediction. So we will assume an initial prediction of 15 degrees Celsius. And we'll assume that the state error covariance starts at 0.5. So that means the error we expect in our first prediction is going to be 0.5. And our measurement covariance is 0.8. Remember that the measurement covariance is how noisy our sensor is, and the state error covariance is how much we trust our predictions. So again, this is a simple Kalman filter example, so you can gain an appreciation of the Kalman filter. Okay, let's start doing some calculations. Okay, so in our little noisy thermometer example, we have our raw readings. So the raw readings are what we read from the thermometer. The noisy thermometer, we have 14.15, 15.62, 15.12, 14.85, 15.93. These are just random values that are close to 15 that I just chose. And hopefully after this example, we'll graph and we'll see that the Kalman filter does indeed improve and filter out these values. Now, some initialization values. We said X initialized is 15, so our initial prediction is 15 degrees. P in it, which is our state error covariance, is 0.5, and then R, which is our measurement error covariance, is 0.8. Now, these are relatively arbitrary values I've chosen. I didn't do anything specific to get these values. They're arbitrarily chosen. And of course, later in this lecture series, we'll look at how to actually choose them. And then we have our equations, which we've had from the last lecture, all 5 equations. So let's start doing some calculations. I'll get orange pen. So let's look at the first step. X predicted equals F times X previous estimate. So X predicted equals F times X previous estimate. Now we said that F is the model, or if you remember, is the model. Now we also want to, in our assumptions, we said we want a constant model. So in a constant model, we actually remove F because F equals 1. So if F equals 1, we just remove it. And essentially all you get is X prediction equals X previous estimate. So we don't need any F here because we just said it's 1. It's constant. So if it's constant, our current prediction equals our last estimate. So let's rub that out and do the calculation. Pen. So X prediction equals X previous estimate. And we set our initialization, at time equals 0, our X initialized is 15 degrees. So this is just 15 degrees. Okay, so for the next one, we got P current. So I didn't write current in the last lecture. So I didn't write P current in the last lecture, but P, which is the state error covariance, has a current and a previous value. And I didn't write that in the last lecture, which I should have. But so let's just write that down. So P current equals F squared multiplied by P previous plus this Q value here. So again, remember we're on a constant model. We're at a constant model. So F equals 1. So just remove this entirely. And now Q is, we don't actually have a Q for now. To keep things very nice and simple, we are going to remove the Q. But throughout the lecture series, we'll look at the importance and why Q is actually needed. So we'll just remove that. So we can simplify this to P, so P current basically just equals P previous. Okay, so let's rub out all these squiggly lines. Bad writing. So P current equals P previous. And we just said that P is initialized at 0.5. So that's just 0.5. Now let's look at this equation here, the Kalman gain. So K is for Kalman gain. And we just say Kalman gain equals P current divided by P plus R. So relatively simple. So K equals P current divided by P current plus R. Remember, R is our measurement error covariance. How noisy is our sensor essentially? So let's just calculate that. That's 0.5 divided by 0.5 plus, we said R equals 0.8. Now I've already done the calculation, but I calculated 0.38, and I'm doing all the calculations to 2 decimal points. So 2 decimal places. So K equals 0.38. Now our fourth step here is X estimate equals X prediction plus Kalman gain times the measurement minus the prediction. So let's do that. So X estimate equals X prediction plus the Kalman gain, Z, which is our measurement, plus X predicted. And so let's calculate that. So what's our X prediction? So we've already predicted X. So sorry, we've already done what X predicted is, and that's calculated in the first step here. And we calculated 15. So we do 15 plus K. What's K? We just did that in the third step, 0.38. And what is Z? So Z is now our measurements here. So I should just write that here, Z. So raw readings are our measurements, are Z. You write 14.15 minus X predicted, which again we calculated here, minus 15. And that amounts to 14.68 at 2 decimal places, that is. So that's step 4 done. Then finally we got to make our next, we need to predict our next state error covariance. So how much will we trust the next prediction? So that is P next equals 1 minus K, or the Kalman gain, multiplied by, again, the current state error covariance, which equals 1 minus 0.38. Should make that decimal a bit clearer. Multiplied by 0.5, and that equals to 0.31. So as for now, we're keeping this simple. So we're only going to keep track of this variable here, so X estimate, and we're going to just write in pink 14.68. And of course you need to keep track of this variable here, so let's keep that on us. And that's the first step done. We've done one time step essentially. It requires 5 equations for that one time step. And now let's do the next one. So I'll delete all that. Probably increase the brush size a little bit so that this gets rubbed out quickly. And I'll keep track of that. So P last or sorry, rather P current it should be now. 0.31. So that's the first time step done. Let's do the next time step. So again, we got to do x predicted, and that was x predicted equals x previous estimate. And again, what's our last prediction? So we've done our initialization step, so which was the last step, and now we have our x predicted. This is our now x predicted, 14.68. Now p current equals f squared. Remember, be a constant model, so just p previous. And then what does our p previous equal? Well, 0.31. So this is the p we calculated in the last one. And actually, I shouldn't write p current. I should write p previous here because that was in the last. So this was calculated from our last time step, and we're going to use this value in our. Oh, that's a bad arrow. And we're going to use that in our current time step. Okay, next is Kalman gain, which equals P current divided by P current plus R, which is just 0.31 divided by 0.31 plus 0.8. That equals to 0.28. If my calculations are right, 0.28. Okay, now we've got to move to the fourth step, and fourth step we're doing the next estimation. So x est equals x predicted plus k z minus x predicted. And remember that x predicted was calculated in our last time step is 14.68 plus k, which remember k is 0.28. K is 0.28. And then we do z. So what is z? Z is the next measurement. So 15.62 minus, again, the estimation. So 14.68. Now, sorry, when I mean the x predicted, I meant referring to this x predicted, not this one here. But yeah, this value here refers to this x predicted we did in our first step. So that equals to 14.94 to 2 decimal places, of course. Now p next, we've got to do our next p, our next state error covariance. We do 1 minus k multiplied by the p current, and p current is 0.31. Oh, sorry, let me just write the equation. Current, and that equals to 1 minus k. Our k is our Kalman gain, remember, and that is 0.28 multiplied by p current, and remember p current is, we calculate here, 0.31, and that goes to 0.22. So again, we're just going to keep track of this variable here. It's our x estimate. So now our next time step, we had 14 point, oh, sorry, I should write that in pink. So pink, 14.94. So that is what we calculated in this current. This is our current estimate for output of the Kalman filter is 14.94. And I'm just going to rub this all out. And of course, I need to keep track of this variable here, which is our p next. So this is p for the next cycle. So let's just update this part here. So I'll rub that out. So remember, our p current is now going to be, what was that, 0.22? Yeah, 0.22. Okay, so now in this third time step, I'm not going to write all the equations down because I'm sure you already understand the point, and I'm just going to write down all the calculations I've done. So that's x predicted equals, remember, the previous estimate, which I've calculated as 14.94. Well, rather, I'm using this one here. That's our previous estimate. Okay. Okay. Next one is P current. Remember, P current is the model. We have no model. We have no Q. We haven't got this variable here. We just have PS, P previous, which we've said is here, 0.22. Then K is the Kalman gain. That is the state error covariance divided by the state error covariance plus the measurement covariance, which I have calculated as 0.21. And now we do our estimate. X estimate equals the X prediction plus a Kalman gain times the measurement minus the X prediction. Remember, you must use this measurement now. Z is now this. And I've estimated that to be 14.98. So we can write 14.98 here. And then, of course, we got to do our P next. What's our next state error covariance? And that's 1 minus the Kalman gain, which we've calculated here, times the P current, the current state error covariance, which is over here. So that will be calculated as 0.17. And so then that's the third time step complete. Now I'm going to remember this value here. And then I'll rub this all out and we can do the fourth one. So remember, again, we've done the third time step here, and now we're on to the fourth time step. So again, X predicted. We just repeat these 5 steps again and again at every time step. So I've done X predicted, which is just this value here, which is 14.98. Now remember that the reason I'm using just 14.98 here is because it's a constant model, so F is just 1. Now obviously in a more complex example, which actually has a proper model, you can't simply just use 14.98. You have to multiply it by a model or a big matrix. I say big because they usually are, they can be quite sizey. And of course, if you had a model, we probably wouldn't be hand calculating this because it would take basically forever to do. So then we do our state error covariance, which is again F squared. There is no model, there is no Q, just the previous the previous state error covariance, which is 0.17. Yeah, 0.17. Okay, now we just do our Kalman gain, and K equals the state error current one divided by the current state error covariance plus the measurement error covariance, which is again 0.8. Stays at 0.8. And that is 0.18. I calculated that, 0.18. Then our X estimate. Remember, we're using X prediction from here. That's our X prediction. And then the K, Kalman gain, 0.18. And then our measurement. For this measurement, we're going to use this measurement here. So please be aware that you're using the right measurement. And that is 14.96 that I've calculated here. Then we do our P next. And P next is simply just the 1 minus the Kalman gain, which we've calculated here, times the P current, which we calculated over here, and that is 0.13, or 14 rather, to 2 decimal places, 14. And so here, remember, we just record whatever was found here. So that is 14.96. Okay, now for the 5th time, we're going to do for the 5th time step. Can you see how Kalman filtering just uses these 5 equations, and every time step it's repeating these equations? That's simply all a Kalman filter does. Now let's rub that all out. And I need to make sure I have saved this value here. There's P next, so orange. So P current now equals 0.14. Okay, and then let's do the calculations for that. Okay, yep, x predicted. So x predicted, remember that just simply equals the last prediction. Sorry, that equals the last estimate rather, and that's 14.96. Remember, we're using a constant model, so we can just use the last one. And then obviously if you have a model, you have to deal with the model. And then the state error covariance. Let me try and spell that right. Current equals, again, f squared, no model, no q, just a previous one, previous state error covariance, which is 0.14. I think in my calculation I did 139, but should be close enough. Okay, and then into the Kalman gain. So again, we just use Kalman gain is the current state error covariance divided by Kalman gain equals the current state error covariance divided by the current state error covariance plus the measurement error covariance. Quite wordy that is, but I calculated that as 0.15. Now x estimate, that's our fourth step. And remember, our x estimate uses our prediction here. So this is our prediction, and then our Kalman gain here, and then the measurement. So we're on the fifth time step, so we're using the fifth measurement, which can be found here. So remember to use this on the fifth time step, and that is calculated as 15.11. Yeah, 11 to 2 decimal places. And then finally, we have to do our next state error covariance, which is, that is next. Yeah, apologies. And that is just, remember, 1 minus the Kalman gain here times the P current. So that is, remember, P current is calculated here. I put that as 0.12. And we're just storing this value here. This one goes into this array here. And that is 15.11. So these are all the calculations required for a very simple constant model Kalman filter for a single variable. Yeah, now hopefully that all made sense. I'm going to now graph these two arrays here. So these bunch of values here, I'm going to graph them, show you in a graph how a Kalman filter actually does actually filter quite well. Let's just plot these and I'll show you what it looks like. Okay, so we've done pages and pages of hand calculations, and this is the output I've graphed here in Python. So the red is the raw measurements, which you can see quite spiky, noisy thermometer data. That's the red line here. And then the blue line here is a Kalman filter, is the output of the Kalman filter. Now you can see that even though the red line or the noisy thermometer data is quite noisy actually, and there's got two massive spikes here, one big spike here, one big spike here. The Kalman filter smoothed it out quite nicely. So hopefully after the calculations, you can appreciate the Kalman filter a little bit more, because even for a simple example of a constant model, we are actually able to smooth it out quite nicely. Now some thoughts. Now the value of R, or the measurement noise covariance, which we said was R, was put to 0.8 if you remember. Now what happens if the sensor was actually noisier than that? What happens if it was more spiky and more weird and problematic than that? Well, for our simple example, we could simply just increase the measurement noise covariance. So for this simple example of our single variable Kalman filter, we could just increase the measurement noise covariance. But what happens if the sensor value drifts over time? So in here you can see that we just have spiky values here. These are all spiky noise, jitter. We just call it jitter, or high frequency noise. But what happens if the sensor value was slowly increasing over time to 16, 17, 18, 19 degrees, even though the actual temperature was a constant 15? Well, our model does not consider this at all, and our Kalman filter will fail to filter this correctly. So for very, very low frequency noise, our model is not suitable for it at all. Again, not a very realistic model used at all, but anything with variables, a more complex model, will take forever to write by hand. So for now, we just stick to a simple model. A simple constant model. However, hopefully it provides some understanding on the basics of Kalman filtering. So now you should have a little bit of an appreciation for it, and we can move on. So The next video, we're going to write up a Python simulation of the simple Kalman filter, actually the same Kalman filter used today, and slowly over the lecture series, we'll keep improving this Python simulation so that you can learn more about the different variables and parts of the Kalman filter and their importance. But specifically for next lecture, we'll use that simulation to understand the importance of initialization values. So today we started x initialized at 15 degrees. What happens if you start at 0 degrees or 1 degrees or 100 degrees? Otherwise, thank you and please stay safe. I hope to see you in the next lecture. Goodbye.